two pieces. We have time, changing with time, but at any point in space at a given time, it's the same. So what we have here basically, we'll have a three-dimensional space of constant curvature, which is what we just solved before. Okay? But it's changing with time. So at any given time, it's the same everywhere. The next instance is also the same everywhere, but a little bit different than it was before. A little bit further apart everywhere. What would the metric look like? We're going to write down the metric for the three-dimensional space of the universe. It's going to be dr squared multiplied by that factor of 1 over 1 plus kr squared, plus r squared d theta squared plus r squared sine squared d phi squared. That's it. We just kind of give the answer. It's very simple. If we assume that the universe is the same everywhere in every direction, then this is the way it is. So what we have here basically, we'll have a three-dimensional space of constant curvature, which is what we just solved before. Changing with time, but at any point in space at a given time, it's the same. Now, we could write that metric differently for the same given physics, right? But this is one convenient way of writing it for that situation. What are we going to say? In that physical three-dimensional space, the distance between any 2 points is going to change with time. It's going to be a function of time. Forget about the dt squared part. Just look at the second part. You have r squared of t, some function of time, multiplying this whole spatial thing. What is the spatial thing in the square brackets? It's that three-dimensional space of constant curvature that we just solved.